This is a video of integrating factor for differential equation, and it's a special case. It's a lot simpler and easier than the general case was just discussed in part 1. So in the summary, that this curl, the integrating factor is calculated in the following way. There's this curl, non-zero case is what we're looking at, and we have to find this coefficient and realize it as a partials of this of some function j. And you can quickly check that using the Clairaut's theorem. Then once you find j, and if you raise that to the exponential power, then that's the integrating function. That's going to do the magic. If you looked at the example we did earlier, and that simplest case is that this will be a 0. Let me show you the condition. The simple case is the following. We're looking at this equation in simpler form, a and b. So if you simply set this jy, this whole thing, part to 0, and we expect this by here is to be 0 as well. So when we differentiate it with respect to y being 0, it must be everything in terms of x. So here is a jy, we set equal to 0 and see what happens. And jx had no choice to jx because this entire thing is 0. Jx must be this whole quantity divided by n. But because of this condition, had to satisfy this Clairaut's theorem, this function here, jx, which is completely determined, must have a derivative 0 with respect to y. So this one has only x in it, so that when you differentiate with respect to y, it becomes 0. So this Clairaut's theorem puts this condition that whatever you're looking at here, the curl divided by n, that came from the setting, must be solely in terms of x. That's the case, it's satisfied this condition. Therefore, we'll be able to compute j. J is simply the antiderivative of this one with respect to x. So I use this capital G and raise to this exponential function. Same case here, if you put this one to 0, then this one will be 0, because that matches that b is that jx. And we want that thing to be 0 as well, but this is differentiated with respect to x. Therefore, we're putting the condition, this jy, whatever that is, that's actually had to be this quantity right there. Jy must be solely function of y, such that when you differentiate that thing with respect to x, it becomes 0 plus 0 to 0. So checks that Clairaut's condition. So if this curl divided by m is a solely function of y, then you put that negative because of this negative symbol is float around here. Your j will be simply this antiderivative of this with a negative. So that's antiderivative with respect to y, and integrating factor just appears as this exponential part. So if this happens, the computing integrating factor is easy, and because putting this 1 0 0 there, this is some special case and strong condition we're imposing. So let's look at some example that this happens. So this is example we have. It's not homogeneous, it's not easily separable. So this is a perfect example, the necessity of our integrating factor technique. So I'm assuming that you've watched the part 1, it's a more general case. So I'm just gonna say that if you compute the curl of this one is y minus x. So that's gonna go to the numerator. So we're gonna consider divided by n and divided by m and see if that ends up at a correct function. So the way I memorize this one is that if you divide it by n, so you look at it right next to it, and x is supposed to be function in terms of x. When you divide it by m, what's m here? My, so it has to be ny. That's how I would remember the variable. So I'm trying n here. This is what's computed, y minus x. It's y minus x. And n here was x squared minus xy. But I factor it out so that I can compare with the y minus x. Obviously, these two cancel with this negative 1. So that's your gx. And it is gx because there's only one x. There's no y appeared in there. So what is the antiderivative of this one? And it turns out it's ln 1 over x. That's the antiderivative of this one. So if you put that into the exponential form to get I, which is supposed to be this, I is e to the g, g is the antiderivative of this one. Then this whole thing goes up there, and ln and e cancel, it becomes 1 over x. That's your integrating factor. It is saying if you multiply 1 over x here and there, you'll be able to see their exact. It was this simple, and still it's not easy to see. So here I actually multiplied this integrating factor, multiplied there, so that gives you y, that's 1 over x. Multiply here, that gives you x, that gives you y. Then I'm not going to check if it's exact, I'm just going to go ahead and actually integrate, and I'll be successful because it's supposed to work. Here I'm integrating this part first, so the difficulty of integrating here and there is kind of about the same. So, but sometimes integrating this one first is more accessible. In that case, you have to do that. So here's integral. That one integrated with respect to x is going to be yx, and that's negative ln x. And again, it's relative constant. It has to be something in terms of y. So now you have to use what's in front of here. We haven't used this one, so you compare that. This one is supposed to be y derivative of this one. So I'm doing that. If you do that, you have x. That becomes 0. That's phi prime of y. So that should match exactly this form. So good, this x is matched here. So this one must be negative y. But what could be that phi? That was the antiderivative of negative y. So in that, phi turns out to negative 1/2 y squared plus this absolute constant. So here is that solution right there. So yx, negative ln x minus this phi part. So if you actually differentiate that with respect to x, you're going to get that. With respect to y, you're going to get that. And that's the general solution. If you have initial condition, and if you put it in there, that'll determine what this c should be.